Second speaker this morning is Isaac Goldbring, who will speak on undecidability of QWEP. And there will be a short announcement after his talk.
Okay, well, thank you very much to Brad and Ilias for inviting me. It's a pleasure to be here. I should say yesterday, watching three operator algebraists talk about model theory made my heart melt. It was amazing. I'm used to being the one who's going to their meetings and afraid I'm going to say the words wrong. So it was nice to see them talking to us and afraid they're going to use the words incorrectly. But I think it's an example that this field is thriving, and there's a really beautiful interaction between model theory and logic more generally and operator algebras, and I hope that continues. I've been approached by several people saying, I think this stuff is interesting. How do I enter this field? And I've constantly said, yeah, that's kind of a tough question to answer. If you're a logician, learning operator algebras is tough. If you're an operator algebraist, learning logic is very easy, so just go do it, and then you can start working with us. But truth be told, there really was no entry point. So let me start with a shameless plug. Hot off the presses, there is a book, a volume that I edited. Many of the authors are in this room, actually, which is meant to help people who want to get into the field first learn whatever it is they're missing. If you're the logician and you don't know much operator algebras, there are beautiful surveys on von Neumann algebra, beautiful introductory surveys on von Neumann algebras and C-star algebras written by Adrian and Gabor. There's a just phenomenal introduction to continuous model theory written by yours truly, Brad. And then a ton of just survey articles about what's been done and what we would like to see done. There's a emphasis on open problems. So if you have a student who wants to get involved or wants to get into the subject, I highly recommend this. All right, that's enough shameless advertising. Let's begin the talk. So Magdalena really helped me out, and she introduced many of the concepts, not all, but many of the concepts I'm going to need in my talk. But the overall theme of the talk is undecidability and how, besides getting the failure of Kahn embedding, MIP star equals RE really has a lot of undecidability results. And that's, I want to talk about these results. Oh, I should have said the majority of this work is joint with Brad and his student Jan, although a few bits at the end are just Brad and myself. Okay, so let me talk about this Kirchberg QWEP property, which was kind of in the background in Magdalena's talk, but she didn't really say it in full detail. And really, it starts with this weak expectation property of Lance, which stems from this issue with C-star tensor products. So, you know, if you have an inclusion of C-star algebras, A inside of B, and some third algebra C, you would hope that you would get an induced inclusion A tensor C inside of B tensor C, which you do if you're talking about the min tensor product. But for the max tensor product, the canonical map you get just from the universal property coming from the max tensor product need not be an inclusion. Okay, so I didn't write it on the slide, although I will mention it later, so might as well say it now. When A sitting inside of B has the property that no matter what C you max tensor with, you get an inclusion, this is called a relatively weakly injective, RWI inclusion. And you say C-star algebra A has the weak expectation property if this problem isn't a problem. So no matter what extension of A you look at, and no matter what C you try to tensor with, the natural map is an isometric inclusion. Okay. And so in this fundamental paper of Kirchberg that Magdalena was referring to, he proves this nice sort of test for how you can check if something has the weak expectation property. You check if there's a unique tensor product of it with C star of F infinity. C star of F infinity is like the tester for whether or not you have QWEP. And in the same paper, he shows B of H has the analogous relationship with the local lifting property, and he proves this results that there is a unique tensor with B of H and C star of F. Okay, So then you look at this and you go, okay, well, what if I plug A in for A, C star of F infinity? Do you have a unique norm tensor product on C star of F infinity with itself? In other words, does C star of F infinity have the weak expectation property? You can show for the reduced C star algebra this is false, but it's at the time it was not known. What about the universal C star algebra? Okay, so here's a silly statement. If C star of F infinity has the weak expectation property, then every separable C star algebra is a quotient of a C star algebra with the weak expectation property. Okay. And so you say, when that's the case, when a algebra is a quotient of something with the weak expectation property, you say it has the QWEP, it is QWEP. I don't know what the correct English is, but QWEP. Okay. But then Kirchberg proved something which is definitely not silly, namely when C star of F infinity has the WEP, that's equivalent to every C star algebra having the QWEP. So I just mentioned 1 implies 2. Yeah, I didn't. 2 does not have a separability assumption, but that's not an issue. 2 implies 1 would tell you C star of F infinity has the QWEP, but it also has something called the lifting property, which allows you to remove the Q and just get the WEP. But the real bulk of the theorem, the real heart of the matter, is that these statements are equivalent to the Kahn embedding problem, having a positive solution. Okay. And a key ingredient in the proof is that for a tracial von Neumann algebra, having the QWEP is equivalent to being Kahn embeddable. Okay. So there's a trace preserving embedding into the ultra power of R. I mean, there's more to be done because it's kind of miraculous. How could something about all C star algebras get you something about just tracial von Neumann algebras? I mean, the way you go from a C star algebra to a von Neumann algebra by taking the double dual, that's hardly ever finite. So how in the world does just knowing this about the finite realm somehow get it for all C star algebras? There's lots of ingredients involved, but the one that I want us to remember is just this one ingredient about for tracial von Neumann algebras, QWEP is equivalent to Kahn embeddability.
What is the definition of QWEP for von Neumann algebra?
It's a C star algebra, so it's the same. Okay.
Or you can say the definition is that it's Kahn embeddable.
Yeah, but it's important to know what it means for like a non-tracial von Neumann algebra to be QWEP in this story. It's important to know. Yeah.
It's a non-separable C star algebra, so how can it be a quotient of it's a non-separable C star algebra, so how can it be a quotient of a separable C star algebra?
I didn't say that.
Well, sorry, I'm falling behind.
So if C star of F infinity has the WEP, then every separable one has the QWEP, but you can go from every separable one having the QWEP to all of them having the QWEP. That's not so hard.
Okay, but how can the tracial von Neumann algebra have the QWEP? Oh, I see. That's all right. I have to wrap my mind around.
And by the way, Kahn embedding, talking about separability is irrelevant, right? So Kahn embedding is any tracial von Neumann algebra, separable or otherwise, embeds into an ultra power of the hyperfinite. If your tracial von Neumann algebra is not separable, okay, the ultra power lives on some uncountable set, but it doesn't change anything. Okay.
Sorry, one more question is that the infinity stands for countable.
There the infinity does stand for all if not many generators, yes. Yeah. Okay. So just to give you an idea, from the logic perspective, what's the difference between the WEP and the QWEP? So Thomas, who fled, Thomas and I in 2017 examined, amongst other things in this paper, the model theoretic content of the WEP. And we showed that it's equivalent to some weird hybrid EC statement. So you had Adrian's talk yesterday about EC things. Having the WEP is an EC type thing, except you're talking about C star algebras being inside of other C star algebras. Okay, but you're not requiring them to be EC as C-star algebras, you're requiring them to be EC just as operator systems, and not with respect to all formulae, but just positive formulae. So whatever any of that means, it's some kind of EC type property, but it's not an axiomatizable property. We showed that if the ultra power of a C-star algebra has the QWEP, it was because the algebra itself was subhomogeneous, which is an axiomatizable property. It's a very special property of C-star algebra. So it basically never happens in general. If you have something QWEP but not subhomogeneous, its ultra power won't have QWEP. It's not axiomatizable. On the other hand, in an earlier paper, I observed that being QWEP is an axiomatizable property, which is weird. It's kind of a weirder property than the QWEP, but yet it's better behaved from the model theoretic perspective. And the proof uses soft semantic techniques. This is the kind of thing that maybe units might say is like black magic, right? When he hears me talk about Levenheim's Skolem and stuff like this. There is a test for when a class of structures in a language is axiomatizable that does not require you to actually write down the axioms, because you may just not know how to do that. So what do? You check that the class is closed under isomorphism. Clearly not a problem here. Ultra products, Kirchberg basically did that for us. And ultra roots. Ultra roots say if an ultra power has the QWEP, then the thing itself has the QWEP. Something sitting inside of its ultra power is an example of one of these RWI inclusions. And Kirchberg showed if something has QWEP, then so does anything RWI inside of it. Okay? So super soft. I thought I speculated in the paper, and then I actually went back and read my paper, and I didn't, but I should have speculated for like concrete axioms. What are the concrete axioms for being QWEP? The first result in this talk is to show that if I had been smart enough to speculate in that paper, what are the concrete axioms, I would have not been able to, because you can't. If by concrete you mean effective axioms. And this is a consequence of MIP star equals RE. So this is the first thing I want to explain. Are there any questions at this stage? Yeah. Yes. Yes. So it is AE axiomatizable. Okay, yes. Yes. Just not effectively so. Yeah. Okay. So the starting point is to first explain the connection between con embedding and MIP star equals RE that Brad and I discovered. So Brad is braver than I am, and Brad and I thought we had a proof of what I'm about to say, and then he went and decided to talk about it in front of a bunch of people. I think it was here even, if I'm not mistaken, the Canadian Operator Algebra Symposium. And I said, Brad, we don't have a proof yet. He's like, it's okay, I'll just talk about it. And he did. But we didn't. I was right. We did not have a proof. But it was actually very fortuitous that he went ahead and did it anyways, because some smart people were in the audience, such as like Chris Schaffhauser, and I think, I don't remember if Vern was there or not, but they came up to him afterwards and they're like, oh, I bet you could do what you're trying to do if you just use our results, so and so and so and so. And they were spot on. And that's exactly what we did. There were definitely things to do on top of that, but that was certainly the key insight to fix our quasi-proof. So what a quasi-proof of what? So we proved the following result. If you look at the hyperfinite 2-1 factor, viewed as a structure in the language of Tracial von Neumann algebras, and you talk about its universal theory, then it's not computable. What does that mean? There is no algorithm so that upon input, some universal sentence in the language, and you might go continuous logic, there's uncountably many formulae. What do you mean input? There's an effective countable list of sentences that is dense. It's good enough. Give me one of those, plug it into the computer, and you give me an error, a rational error, let's say, and then the computer should give me some interval of radius less than that error, and the truth value is in that. Okay, so I can effectively approximate the truth value sentences. You can't do that. That's the theorem. one of the things when people ask me about model theory of operator algebras, one of the things you have to change in your head if you're like an ordinary model theorist is everything in ordinary model theory is beautiful from the model theoretic perspective. Everything is decidable and you can understand all its models and quantifier eliminated. None of that happens in operator algebras. And that's actually a good thing because that's really not what we're up to. I think, at least not what I'm up to. I want to use model theoretic methods as a tool in operator algebraic endeavors. And I'm not so concerned with the fact that from the model theoretic perspective, these things are horrific. Okay? To give you an idea of how they're horrific, your superstar, your hyperfinite 2-1 factor, the things you all hang your hats on, its one quantifier theory is undecidable. Right? Whereas in ordinary model theory, all of our crazy groups and rings and fields or whatever have decidable complete theories. It couldn't be drastically more different. Okay, so the proof, as I said, uses MIP star equals RE, and these operator algebraic results that Magdalena mentioned in her talk, specifically the fact that these synchronous correlations have this purely operator algebraic presentation, which fits exactly into the model theoretic framework. There's one tiny thing, you have to be quantifying over PVMs. And one of the complaints classical model theorists have about continuous model theory is they say your notion of definable set is really complicated and strange and weird. You guys got it wrong. And this is the example I use to tell them, no, the forefathers of continuous model theory got it exactly right. Because here's an example in nature where I needed to soup over PVMs. I could only do that if PVMs form a definable set. And they do because Kim, Paulson, and Schaffhauser in their paper prove that as a lemma. The lemma right before the main theorem. Of course, they don't call it a definable set because I don't think they knew what a definable set was, but that's exactly what they verified. And then Brad and I had to go, uh-oh, but when you convert quantifying over a definable set into a legitimate formula, that needs to be done effectively because everything I'm up to here, I'm concerned with effective matters. So there are things to check and do, but this is a beautiful confluence of the operator algebras and the model theory coming together. Okay, and Brad and I had already observed in 2016 that if Kahn embedding was true, then the universal theory of R would be computable. That's actually a pretty easy standard thing to get. And so this gives you, at least in our modest opinion, a more concrete refutation of Kahn embedding from the failure of MIP star equals RE, and it comes with extra bells and whistles that I'm not going to talk about now. Okay, but the takeaway is that at least in the tracial von Neumann algebra realm, being QWEP is not effectively axiomatizable. Okay? Because being QWEP is exactly the universal theory of R, and that's not a computable thing. And we want to upgrade this result not just for arbitrary tracial von Neumann algebras, but to all C-star algebras. So certainly with zero jump, it can solve it. Zero jump can, and your guys' result shows zero cannot. Yeah. Other questions? We don't know if R is AE axiomatizable, right? Is that what you're saying? Oh no, you're asking about the two quantifier theory. Yeah, so it's wide open. Yeah. Yeah. Yeah, so that would be right. So basically, the one quantifier theory, you need one jump. Do you need two jumps for the two quantifier theory, for example? We don't know. Other questions? Okay. So here's our first main theorem. And actually, yeah, Brad made a funny joke in an email with myself and Jan, because while writing the talk, I noticed a mistake in the proof of this theorem, which wasn't a drastic mistake. And in fact, upon fixing it, made the theorem better. So this is the better, hopefully correct, we'll see, I'll write the proof, you'll tell me if it's correct, correct version of the theorem. It says, in the language of C-star algebras, there is no effectively enumerable theory, all of whose models have the QWEP, and which has a single model that's infinite dimensional, monotracial, and for which that unique trace is faithful. So we had some stuff about the uniform Dix-Mier property. It was kind of remnants from the other paper I was mentioning where we did need the uniform Dix-Mier property and we weren't really paying careful attention. And it turns out this assumption number 2 here is much more mild, okay, than what we had initially assumed. But in particular, there is no effective theory that axiomatizes being QWEP. If you try to write down axioms which capture exactly the QWEP ones, it can't do it because it would be an example of the T that I have up here. So you can't effectively axiomatize being QWEP. All right, so how does the proof go? Suppose towards a contradiction you had such a theory. So all its models are QWEP, and it has at least one model A, infinite, monotracial, and the unique trace is faithful. So what do? I go to the language of tracial C-star algebras. So the language of C-star algebras equipped with an extra predicate whose intended interpretation is to be a trace. I write down the axioms, which just say tracial C-star algebras. That's effective. And then I add to that this purported T. Let's call that T prime. Okay. And then by assumption, A with its unique trace is a model of T prime. Now I claim if I take any universal sentence whatsoever in the language of tracial von Neumann algebras, and I look at all models of T prime, so they're of the form C-star algebra, comma, a trace on it, and I evaluate that universal sentence in such a thing, the soup of all such answers is the same as the sentence evaluated in the hyperfinite 2-1 form. So the forward direction, the greater than or equal to direction just follows from the fact that if I take this specific model A I asked about, and I look at its GNS completion, then because the trace was faithful, A sits inside of it. And because it was infinite dimensional and monotracial, the GNS is a 2-1 factor. So the trace the value of sigma in M is at least the value of sigma in R, because it's a universal sentence. And I claim that no matter what, the value of the sentence in A and in its GNS are the same. Okay? So the reason that it's the same is that, well, first of all, A is SOT dense in M. But also, since I'm just asking about sentences in the tracial von Neumann algebra language, they don't mention the norm, the operator norm. The way the GNS works, right, is that the trace on A and the trace of the image of A in the GNS the same. So the trace could, in theory, only go up in the GNS, but because A is SOT dense in the GNS, it's actually equal. And for the less than or equal, if I take any such model and I look at the GNS, then because the C-star algebra was QWEP, its GNS is also QWEP. And therefore satisfies con-embedding. And therefore embeds in the ultra power of R. So the value of the universal sentence in N is no more than the value in R. But once you believe this equality I've displayed here, then it's the same argument as Brad and I had earlier. This soup is the same as the inf of the upper bounds you could derive for the sentence from T prime. And so you would then be able to derive upper bounds, a convergent sequence of upper bounds, computable upper bounds to the value of sigma in the hyperfinite, which is exactly what Brad and I showed you cannot do. So following from MIP star equals RE. Okay, so that's the proof. QWEP is not effective. Okay. Then in the same paper, we also prove, besides some C-star algebra results like that, some type 3 results. Now here's where I pretend that I know what I'm talking about concerning type 3 things. So what's a W-star algebra? It's a von Neumann algebra equipped with a faithful normal state. So it's a particular kind of non-commutative probability space. Tracial von Neumann algebras are examples. And then the appropriate notion of embedding between two such things is a star homomorphism that admits a state-preserving conditional expectation, which that's automatic in the tracial von Neumann algebra case, but not automatic in general here. Okay. Now there is a natural ultraproduct construction for these things called the Ocknianu ultraproduct. It is the tracial von Neumann algebra ultraproduct when you're talking about tracial von Neumann algebras. Yeah.
Since there already are W star algebras, so it seems to me you could call this a pointed W star algebra.
Why pointed?
Well, because it comes with normally the W star algebra is just a Neumann algebra.
Sorry. Okay, sorry, thank you. W star probability space, sorry, is what I meant to write. Excuse me, sorry. Thank you. Definitely a major typo, excuse me. W star probability space is what I meant to write. Thank you. Okay, so, and see, then I did write the right thing later, okay. Okay, there are at least 2 different languages for studying these things model theoretically. Dabrowski was the first to write down axioms. If you want to torture a student, you say, go read Dabrowski's paper and look at these axioms. They are frightening. And we have tried to read them. That is their virtue. They are effective, yes. Well, they can be made to be effective. I think that's part of the content of what we were talking. He uses all functions that you can take derivatives, blah, blah, but you don't need all of them. You just need effective ones. And so they can be made to be effective. There's an alternate approach that Brad Thomas and I had, which is much simpler. But then one of the things that we're currently tinkering with, and we're pretty sure we know how to do it, is you want to get the modular automorphism group involved in there, and you want to do it in an effective way. And so we think we know how to do that. But in any event, this can be done. There is a model theory. Okay, and then rather than talking about the hyperfinite 2-1 factor, we're going to be talking about type 3 versions of it. So for those of you in the know, you know already that there are type 3 versions of the hyperfinite 2-1 factor. So for lambda between 0 and 1, the type 3 lambda version is the powers factor, and it has a particular state that's important on it called the power state. Here's one way of representing it as an infinite tensor product of matrix algebras. And again, this is me pretending like I know exactly why all this works, but if you replace 2x2s with 3x3s and you do some other fiddling, you can get a type 3-1 factor, the unique hyperfinite type 3-1 factor this way, and it's called R infinity. And like any type 3-1 factor, any 2 faithful normal states on them will yield W star probability spaces with the same theory. They'll be elementarily equivalent. In other words, their Ocknianu ultraproducts will be isomorphic. Cyril and I observed this in a paper we wrote a couple years ago, but this is really just Kohn-Stormer transitivity written down model theoretically, is all this means. So whereas the R lambda, you have to be careful when you tell me which state you're putting on it in order to take the Ocknianu ultraproduct. With R infinity, it doesn't matter. They'll all be the same. Okay. And then Ando, Hagerup, and Winslow had a beautiful result giving you sort of a type 3 analog of Kohn embedding, right? So for tracial von Neumann algebra embedding, Kohn embedding says, do you embed into the tracial ultrapower of the hyperfinite 2-1 factor? What they show is for a separably acting von Neumann algebra M, it has QWEP precisely when it embeds into the Ocknianu ultrapower of the hyperfinite type 3 lambda factor where you use the power state, and that's also equivalent to embedding into the Uknion ultra power of R infinity, the unique type 3 lambda 1, so the type 3-1 hyperfinite, where I didn't have to tell you what the state was because it doesn't matter. They're all, the ultra powers are all isomorphic. Okay, so this is a nice result. And then just from the model theoretic perspective, what this tells you is, this tells you a W star probability space has QWEP, where by that I mean the underlying von Neumann algebra has QWEP, precisely when it's a model of the universal theory of R infinity in either of the two languages I described. So it's an exact parallel to the tracial von Neumann algebra situation. Okay. And so we proved some undecidability results in this context as well. So we proved that there's no effectively enumerable set of sentences in the language of W star probability spaces, and I'm being vague here, which language? Either of the two. We settle it for either of the two approaches I mentioned, that precisely axiomatizes being QWEP. It's not like, it doesn't immediately follow from either of the results I mentioned earlier, the tracial von Neumann one or the C star one, because the languages are different. And in particular, then you get a type 3-1 version of our earlier result, namely that the universal theory of R infinity is not computable. Okay. I didn't know what to write in terms of a proof, because the proof is trivial and annoying at the same time. It's trivial because you say, if I'm a tracial von Neumann algebra, and I look at me as a tracial von Neumann algebra, or if I look at me as a W star probability space, to an operator algebraist, they wouldn't see the difference. But our languages are different, especially if you're using the Dabrowski language, because yes, Dabrowski doesn't actually allow you to multiply in his language. He smears his multiplication because things have to be continuous. So in the tracial von Neumann algebra language, you're allowed to multiply. In the Dabrowski language, you're not allowed to multiply. So this is why I say annoying additional language considerations. So this really is saying, okay, you take our result for the 2-1 factor situation, and then you just make sure the language differences don't cause you problems. And that's what you have to do. No. Wait, yes, because they're closed under ultra powers. Yes, no, they are. What you cannot say is finite von Neumann algebras are, because you can equip them with weird states, and then the ultra products can leave. Yeah. Okay. Right. Then the other thing we prove is that for any lambda, so the first result says the universal theory of R infinity is not computable, and it doesn't matter which state because they all have the same theory. Now for the power state, for the type 3 lambda, I do have to be careful. So I'm being specific, talking about the W star probability space that's R lambda with its power state. That also does not have a computable universal theory. And the proof is different. So what's the key point here? So somehow, again, we have to get tracial von Neumann algebras involved. And it turns out for certain nice kinds of states, the so-called lacunary states, this is some condition about the modular automorphism group, or rather the spectrum of the modular operator, you can prove that the centralizer of the state, so these are all the elements for which the state looks like a trace. It's all the x's for which phi of xy is phi of yx for all y. The centralizer turns out to be a tracial von Neumann algebra. In the case of R lambda with phi lambda, it's exactly the hyperfinite 2-1 factor. And it turns out that if you read the Ando-Hagerup-Winslow paper, they more or less observe, again, not in the same language, but they more or less observe that the centralizer is a definable set. And so I can see it living in the type 3 thing, and I know the undecidability result for the tracial von Neumann algebra setting. So you would hope that because the tracial von Neumann algebra lives definably inside of the type 3 thing, I could just leverage that. And that is essentially the proof. But the Ando-Hagerup-Winslow observation that it's definable is one of these soft arguments, just commuting with ultrapowers. Since everything we're concerned with is effective, you have to write down explicitly how it's a definable set, and you have to make sure you're doing that effectively. So that's where the bulk of the work goes in the proof. Okay. Are there any questions about this slide? Okay. All right. In the remainder of my talk, I want to talk about recent work just with Brad about a property we introduced for C-star algebras that we called the Sørensen property, very much motivated by what Magdalena was talking about in her talk, mainly because I want to advertise some open questions about this notion that we couldn't answer. So let me review some things that Magdalena introduced in her talk. I mean, I didn't know she was going to talk about them, so I had them in my slides. So you're right, you have these quantum spatial correlations. And if I'm not mistaken, I think the roles of N and K are reversed in my talk versus her talk. Apologies for that. Right, so these are the correlations you get for which I think in terms of non-local games. So I think of X and Y as questions that Alice and Bob are being asked. A and B are the answers that they could give. So the way that they go to answer those questions is they have their own Hilbert space for which they're going to make measurements. Alice has hers, HA. Bob has his, HB, finite dimensional. And then they're going to go make quantum measurements on their space. So unlike Magdalena, I'm not assuming they're PVMs. I'm assuming they're POVMs, right? So they're just positive operators that add up to the identity. And Bob has his. And then they share a state of their composite system, the tensor product. And then the way that they go to decide to answer is they each measure. So they go, oh, I was asked X, you were asked Y. Let's take our measurement operators corresponding to those questions, and let's act on our shared vector, and that will tell us the probability that we answered with A and B, respectively. And instead of using the tensor product model, they share a single Hilbert space, but possibly an infinite dimensional one. And to ensure that it doesn't matter who measures first, you assume that their measurement operators commute. If you use that model, that's the quantum commuting model. And as Magdalena mentioned, it's clear that the quantum spatials are inside of the quantum commuting. The quantum commuting are in fact closed, so the closure sits inside of there, and that's what she was calling CQA. I thought the A stood for asymptotic, but she said approximate. Probably both make sense. Okay. Key point for me is that, I mean, there are standard tricks to go from POVM to PVM, but I'm assuming POVM here. Okay, and Sørensen's problem, as she already mentioned, was that the question of are these two sets CQA and CQC the same? And this result that I forgot to attribute, so thankfully she did, so independently Fritz and Junge et al. State that you can characterize when you have one of these correlations based on purely operator algebraic descriptions. So you're looking for POVMs, AX, again, X for the questions you might be asked, and BY, Y for the questions Bob might be asked, in the universal C-star algebra of this free group generated by k things of order n, and a state on either the min tensor product or the max tensor product, depending on whether you're talking about QA or QC, for which the way you're calculating the probability is you're just taking the state applied to this simple tensor. So this is the result that she already mentioned, and this right away tells you why the QWEP problem implies Sørensen's problem, because the QWEP problem tells you that those two tensor products are just isomorphic, so they have the same states. Okay. All right. So one thing that struck us was why not make a similar definition or discussion for arbitrary pairs of C-star algebras, not just this C-star algebra with itself. So we decided to look at the following sets of correlations, which we call C min and C max. Again, depending on the data K and N, but also depending on a pair of C star algebras, C and D, where you do the exact same thing, just now your POVMs live in C and D respectively, and your state lives either on the min or max tensor product. And one thing that we didn't really bother to investigate too much in depth, but we see no reason why in general these sets of correlations would be closed, so we just took the closure just to not worry about these things. Although probably that's worth investigating whether the closures are necessary. They probably are in general. And then at least in Fritz's paper, you can find these statements, probably not in generality for C and D, for C star of FK, or yeah, C star of FKN with itself, but the same proofs work. The min correlations are contained in the max correlations. Every min correlation is a QA correlation, and every max correlation is a QC correlation. These are all sort of standard facts, you know, using GNS or various things. Okay. And so we say that the pair is a Sørensen pair if the min and max correlations are the same. And we say it's a strong Sørensen pair if, in fact, that those two correlations being the same, they're also equal to CQA, right? So they're contained in CQA, but we actually want to get all of CQA that way. So that's when we say the pair is a strong Sørensen pair. Okay. Questions on the definition?
Is this model theory?
Sorry?
It seems to me you're not talking about model theory right now.
Definitely not, but I will be. But I will be. Sometimes I pretend to be an operator algebraist and think about things that are purely operator algebraic, but I promise I will eventually connect them to model theory, to be true to myself. Okay. So Sørensen's problem asks that, of course, if C star of F infinity with itself is a Sørensen pair, and now we know that's not true. I think this terminology is due to PZA, but correct me if I'm wrong. There's a notion of a nuclear pair. So C and D is a nuclear pair if the min and max tensor products are the same. So there's a unique tensor product on the algebraic tensor product C and D. Sorry, a unique C star norm on the algebraic tensor product. Right, so in this language, Kirchberg's result is that your WEP, A is WEP if and only if A C star of F infinity is a nuclear pair. So nuclear pairs are Sørensen pairs because the algebras are isomorphic. So the correlations you get using the states are isomorphic. And what we show is exactly one of the following things happen. Either you're just not a Sørensen pair, or you're a Sørensen pair kind of for a silly reason. One of the two is subhomogeneous, therefore nuclear, and therefore a nuclear pair, but you're not a strong, that forces you to not be a strong Sørensen pair, or you're a strong Sørensen pair and you avoid those trivialities. So we show those are the three options. And then we show that the class of Sørensen pairs is closed under taking quotients. By that I mean if C and D is, if there are C prime and D prime such that they individually quotient onto C and D, and if C prime D prime is a Sørensen pair, CD is a Sørensen pair.
Isn't it obvious that exactly one of the following happens?
It wasn't, so one thing that would be nice is it wasn't, like almost all of it was obvious except one implication, and the only proof we could find uses the main result which appears on the last slide. So if you could, in the middle of a talk, I'm not going to be able to remember which of the implications was the non-trivial one, but if you could find a simpler proof for that, that would make me happy.
I'm sorry, I missed the subhomogeneity.
The subhomogeneity, that's the, okay. Okay, and now that was properties for pairs. I want to go to a single algebra. So I'll say C has the Sørensen property if it's a Sørensen pair with any other C star algebra. Okay. one thing we show is this is equivalent to being a zero sum pair with just C star of F infinity. So this is kind of analogous with QWEP. I can use C star of F infinity as my tester. And it's closed under a bunch of stuff: direct limits, quotients, RWI subalgebras, and ultraproducts. In particular, it's an axiomatizable class. Closure under ultraproducts is kind of a fun proof because it involved two things that aren't super obvious: the ability to take states on an ultraproduct and lift them in an appropriate manner to states on the constituent algebras, and also a recent ultraproduct characterization of the lifting property due to PZA. So these were sort of two of the ingredients. Okay. And then consequently, the QWEP implies the Searle sum property. Because it's inherited by quotients, it's enough to show the WEP implies the Searle sum property. But as I just said, C star of F infinity is a tester for both. So that's why it follows. And this is a question I want to advertise. It's got to be false, but I don't know a proof. Does the Searle sum property imply QWEP? I would really like to see this fall. It's got to be false. I just don't know how to do it. If I have time, I may or may not. I'll advertise one other problem around these things. Okay, and then just like we had strong Searle sum pairs, you can have the strong Searle sum property, which just gets rid of this trivial case when you're subhomogeneous. Equivalently, you're a strong Searle sum pair with everything that's not subhomogeneous. And it's also an axiomatizable property. And if you've been following the theme of my talk, all these axiomatizable properties, are there explicit axioms for them? That's the question we should ask. And then what's the answer I'm going to give you? No. So what we prove is there's no, so the first thing we prove is in the language of pairs of C-star algebras, there's no effectively axiomatizable theory such that all the models are Searle sum pairs. I have to say something else because I could just say abelian. They're all abelian. Okay. So I need some non-triviality condition, and so the non-triviality condition is at least one model is a strong Searle sum pair. As a consequence, going down to single C-star algebras, there's no effectively axiomatizable theory in the language now just of C-star algebras, all of whose models have the Searle sum property, and at least one model has the strong Searle sum property. And in particular, because QWEP implies the Searle sum property, you get an improvement of the result I mentioned with earlier in the talk with Brad and Jan. There's no effectively axiomatizable theory, all of whose models have the QWEP, and at least one model is not subhomogeneous. So earlier in the talk, the non-triviality condition was a model that was infinite dimensional, monotracial, and that unique trace was faithful. Now the non-triviality condition is simply one model that's not subhomogeneous. Okay. So the other two follow kind of immediately from the first one and the fact that QWEP implies the Searle sum property. So I want to just give a hint at how the proof of the theorem goes. So suppose you had such a theory. Again, that means it's a theory in the language of pairs of C-star algebras. All the models have the Searle sum property, and at least one has the strong Searle sum property. I go to an extension of the language where I now have a binary predicate symbol. And what does it do? So the language of pairs has two sorts, one for each C-star algebra. So the symbol takes something from one sort, something from the other sort, and it computes phi of the simple tensor, C tensor D, for some state phi on the max tensor product. And the reason this can be done is because states on the max tensor product, quote unquote, are just extensions of unital linear functionals on the algebraic tensor product that are positive on the algebraic tensor product. And you can write that down in a first order way. So this actually is like effectively, it's easy to write down effective axioms for this. All right, now I have 1 minute left, so I'm going to just assume you have familiarity with non-local games. If you don't, maybe this won't be entirely meaningful to you. So if you have a non-local game G, you can just write down a universal sentence, which is calculating for you the quantum entangled value of the game. So I'm souping here over POVMs and the individual algebras. Pi is the probability distribution on the pairs of questions. D is the decision predicate for the game. And then the correlation, the probability, is now being played, the role of that is being played by this predicate, P. So this is a sentence in the language I've just described. And the assumptions on the theory is just like in one of the earlier proofs, the soup of the value of this sentence on models of T prime is precisely the quantum entangled value of the game. Right? The less than or equal to uses the fact that the models are Sørensen pairs, so the probabilities are being calculated using the max tensor product. But the Sørensen pair property says anything you compute with the max tensor product is a QA correlation. The val star is the soup over the QA correlations. So that's the less than or equal to. And the greater than or equal to uses that at least one model is a strong Sørensen pair. So the correlations I get using that one model are exactly all the QA correlations. So the soup is actually achieved. And now you're in trouble again. T prime is effective, you run proofs, you get computable upper bounds to the quantum entangled value, and that's literally what MIP star equals RE tells you you cannot do. So I think I'll stop there. Here are some references, and I appreciate your attention.